Rojas from Western City University. So he is a professor of pool mathematics and leads the changing posture in mathematics there. Robert got his PhD from the University of Bielefeld in Germany and works on the commutative algebra. He writes books and many papers about the algebras. Today, his talk is an invitation to the algebras. Robert, welcome.
Can I just talk loud? Oh, yeah, okay. I think I just without this, without. Oh, yes, yeah, without. Yes, okay, fine. Thank you. All right, good morning, everybody. My name is Roozbeh, and it's such a great opportunity to be back in Ho Chi Minh. And let me tell you the history. I'm kind of familiar with some of the people here, and I know that there are very strong algebra groups here in Vietnam. And I had the opportunity to meet people in Hanoi and in Ho Chi Minh. So I was at home, and I thought it would be great if we can get together here and discuss some maths. And so I wrote an email to Viet Con, and I was expecting he just ignores me and I don't get any reply back. But then we are here. So thank you so much for that. What I wanted to tell you, and I'm sorry my voice today is not that great, but it's just an invitation to this topic. It's very beautiful topic that it's spreading around, and it was introduced about 20 years ago. And if let me see if I can go. All right, so it's pure algebra, but there is a history of analysis also in the background. So let me introduce. Maybe you recognize von Neumann. He was one of the brilliant mathematicians in 20th century. And maybe you have seen the movie about atomic bombs. This is Oppenheimer. They are in Princeton in this picture. So von Neumann introduced an algebra. It's called algebras of operators when he was looking at quantum physics. So he wanted to develop some mathematics to capture quantum theory. Now, these algebras that he introduced, it's an algebra. So we know algebra, you can add and you can multiply, but at the same time, it has some geometry. So you can say, okay, two elements, what's the distance between the elements? So there is a norm and a topology. Okay, so you can add, you can multiply, but at the same time, you have distances, so a topology. So these are algebras of operators. And people have studied this about, so from 1945 to now. So, and now the trend is that, oops, I'm going backward. The trend is that you don't need the geometry. You can stay on the layer of algebra and it captures a lot of information. So you don't need to have the concept of distances and topology and norm. You stay on the level of algebra. And here is a couple of people. If you are studying algebra, you have heard of the names of Kaplansky, Jacobson. These are heroes, really heroes of algebra in 20th century. And Berberian was the student of Kaplansky. And I really like this quote. It says that if all the functional analysis, all the analysis is taken away, still you have a very rich structure. So that's why we are here to really concentrate on the algebraic part and leave alone the analysis. And there is another quote I saw somewhere else. Let me see if I can go further. Okay, so we are all familiar with the space-time, and the space and time, it always is continuous, right? Space-time is continuous. But the idea is that below this layer, if you just look at the discrete structure, so the algebra, and get a direct limit of the structure, you can really capture space-time. So you don't need the analysis. All right. Now, Leavitt path algebra is one of the examples of this. So you have the system algebra, which has analysis, you have topology, and so on. Leavitt path algebra is just purely algebraic structure, but it captures every properties that you have in analysis. Okay. That was the introduction. Sorry, my voice is not coming up, but that was an introduction. So let me just move on and tell you a very, very nice game. Okay, so at the moment, I'm not talking mathematics, I'm talking about a board game. So you can play at home. So what is this board game? Imagine you have a grid. This is just a grid. And you have 4 objects here. 4 objects. They call it chips. Like in casinos, the chips, right? You can call it chips. The other name for it is sand piles. You'll see in a second what I mean. Okay, so what's the game? Let me explain the game. 4 objects, and you have these edges, right? Let me call these edges in this grid. You're allowed to move each of these objects along this grid, okay? So you move this one along this grid up, this one left, this one right, and this one down, okay? Now, what's the rules of the game? I have to tell you the rules of the game. You're allowed to just move one object along the grid. You cannot just push 2 of them, just one along the grid, okay? That's one. The other rule is that you have to have at least 4 objects, at least the number of these edges objects in order to move them. So you have to have these 2 rules. Remember them? One is that you have to have enough objects, i.e. you have to have the number of these objects and the number of grids should be the same, or there will be more here. And along these, you're allowed to move only one. Okay, so one goes up, one left, right, and so on. You are here. Now, can I move these objects further? Remember the 2 rules. One is that in order to move objects, you have to have at least 1, 2, 3 objects. So I have 1, so I cannot move this anymore. The same story here. I have only 1 object, but I have 3 of these edges, so I cannot move, right? So I get here, and basically the model stops here. It stabilizes. I'm using these fancy words now. So it stabilizes here, right? So the game stops. Great. Let me just do one more exercise and see if you can follow me, because the punchline is very, very interesting. Okay, so forget that. Let's start with this one. You have 4 objects here, 2 objects here, and 2 objects here. These I cannot move because there are 3 edges and there are only 2 objects. I have to have 3. Okay, so I cannot move these. I cannot move these, but I can move these objects. So can you move them? One goes up here, one goes down here, one goes to the left, it becomes 3, one goes to the right, so here. What can I do next? This one is not gonna move. This is also not gonna move, but how about these? Can I move them? Yeah, because there are 3 edges and there are 3 objects. Okay, one goes up, one goes down, one goes back. Okay, the complexity starts here. Now here, one goes up, one goes down, one goes back. So now I'm in this situation. Question, is this stabilized? Is this model stabilized, or I can move further? Stabilized, because look, in the middle, you have 2 objects, 2 chips, if you want to use the terminology, but there are four ways to go, so I cannot. So this is stabilized. Very good. So this is the whole game. This is the whole game. Now imagine you have a very, very big grid. So very, very large grid. And previously I had only 4 objects here. Now imagine you have 1 million of them. Okay, start. By the way, as I go further, I want to start introducing more terminologies. They call it firing. So if this node has these objects and starts moving, I say this node fires. Okay. All right. So now imagine you have 1 million here. 4 of them, one goes up, one goes down, one goes here, one goes here, another 4, another 4, keep doing. At some stage here, there are 4, right? Can you see that in your head? At some stage, you have 4 objects here, then this would fire, right? But 1 million, so, it keeps coming. These chips keeps coming. So at some stage here, there are 4, and you can. Now, here is the question. Can you look at this one? Look at this. I get here. Now, can you imagine in your head, if I keep distributing these objects, I keep doing this, and this is a very large grid, what would be the arrangement in your head? What do you think I would get at the end? Now, in order to give it a shape, what I would do, I would say, look, I'm in a very large grid, but it's look like this. I would say if there are 4, it's gonna fire. Okay, so if it stabilizes, maximum you have 3 objects, right? Can you see that? If something stabilizes, the maximum you have 3, because if you have 4, then it starts again. So you have to have maximum 3. So what I would say is, if you have 3 objects, I put a color, maybe yellow. If there are 2 objects, I put green. If there is 1 object, I put maybe another color, orange. If there is nothing, I put black. Okay, so I can color the grid. I would color the grid. Now, can you imagine in your head what picture I would get if I distribute the 1 million? And it's actually a very nice computer program you can write and show you the animation of this. So I just show you. Here is what you get. And if you look at your computer, you see it's very, very nice. Here, you don't see the beauty that much. On the screen with high resolution, you see much better. So, so you see a fractal. This is called fractal. It's symmetric, but locally symmetric, right? That's what we call a fractal. It's locally, it's very symmetric. So the question is, for example, here is the same color. So I don't remember, but probably they are number 3. So these are all 3 objects sitting here. Here, for example, there are all 2 objects sitting here. The question is, why do you get this shape? Starting from this game you play, why do you get this fractal, which appears everywhere in maths? And nobody knows. With all the technologies, all the maths we have, nobody can explain mathematically why we get this shape. So that's the first question. Can you develop some maybe subject that, as always we do, you push this into that subject and say, okay, because of this, this becomes a fractal. Okay. So again, I want to emphasize, nobody knows. When you move these things, you get such a fractal, such a symmetry. Okay, so where does this come from? Where does this game come from? There are 3 people who wrote this here, Bach, Tong, and Wiesenfeld, in a paper in 1987, and all of these are theoretical physicists. So this person is from Denmark, Tong is from China, and this person is from Germany. And Herr Bach sadly passed away. I'm not sure about the others, but he was basically the champion of this theory. And they wrote a paper, they introduced this game, and they proved only 2 theorems. So you can publish a paper with only 2 theorems. And if you look at the archive, you see how many citations this paper got. You would be surprised to see how many citations this paper got. So now, I tell you both theorems they proved, okay? Both of them I can tell you right now. One of them is, okay. They call these sand pile models because in their imaginations, these are sands moving around, okay? In other books, they call it chips, like in casino. So there are 2 names for it. Now, the first theorem they prove, see if you can see it in your head, is that, look, there are a bunch of chips here, there are a bunch of chips here. So you're allowed to move them, so fire them, right? So I fire this, and then I fire this, good? They prove this is the same as I fired this one first and this one. So the order doesn't matter. I can first, we are doing discrete things, so I have to choose which one. I cannot just do at the same time, like computers. So I fire this first, and then I fire this. Now, the other way around, I fire this and then fire this. The results are the same. Can you see that in your head? Well, they wrote a mathematical proof. The other thing they prove is got stabilization, that once you stabilize this, once you get the stabilization, it's always unique. You always get the same shape. So what does that mean? You might see it from here. That means there was 1 million chips here. As it spreads, okay, and you can see that on YouTube. I have a link somewhere here. So when it spreads, you can just work here. Somebody else might work here, right? So it's up to you where to distribute things. But at the very end, you always get the same picture. So that's the unique distribution. This is the YouTube link, and you see how this moves. It's actually very beautiful. And you always end up with the same picture. So that's called uniquely stabilized. And again, in mathematics, it's always very nice that your presentation is unique. And it gives you a lot of power. Always like in vector spaces, you always have a basis and you can write things uniquely. Here also you can do that. All right. So they prove these 2 and then start this theory. It's called sand pile models. People who are familiar with algebra, now they know what I mean by abelian sand pile models. That refers to being this order doesn't matter, that I first distribute this and vice versa. It doesn't matter in mathematics, you call it abelian. The order doesn't matter. Okay, and good. Then Per Back wrote a book, How Nature Works. I encourage you to get this book. You can actually download this and have a quick look at the book. It's not much maths in there. It's very philosophical. And he argues a lot of things in the nature, how nature works, a lot of things in the nature actually has this behavior. So let me just go down. So traffic jam. If there are 4 cars, one goes up this side, one here, one here, one here. So it's the same behavior. Or the problem, I don't know here in Vietnam, but the problem we have in Australia, bushfire, the forest fire. We have it close to Sydney. The weather is very hot. One tree catches fire, and how does it distribute the fire? Well, the next tree, the next tree, the next tree, the next tree, until it stabilizes. That means that, when destroyed, all that stops. So how nature works, a lot of things behaves like this. COVID, for example, and the people around you, they all get it. So the distribution is like that. And he goes on, and he says, for example, stock market. So have a look, and decide for yourself. Stock markets. or in, I don't know, in your brain, the things work, it has the same sort of behavior, the way things distribute. Okay, now let me tell you here what this means. The science of self-organized criticality, a couple of big words. The science of self-organized criticality. What does that mean? I can explain that also. Okay. First of all, self-organized. What does self-organized mean here in this context? It means if I put 1 million things here, all right, then there is no force from outside. It starts spreading without any force from outside. It keeps doing it itself. So it's self-organized, right? It just does it by itself without any force anymore from outside. Or when a tree catches fire, then it just spreads out without any force from outside. So that's self-organized. It just moves and organizes itself. But what it means, criticality, big word, criticality. It means, okay, it stabilizes, self-organized, it stabilizes. Criticality means it's barely stable. It's stable, but barely. That means if I just add, and I encourage you to look at the YouTube animation, if I just add one chip here, it becomes, what's the word? It's stable. Is that the word? Is stable? Okay. So at the moment it's stable. Only if I just add one chip to this 1 million, it becomes stable. And have a look at the YouTube. It starts moving, and it takes a long time to become stable again. All right. And it's amazing. Again, no math theory behind it. If I start here, just one chip, it becomes unstable and then moves on, and you see a lot of activities here, and then moves here, a lot of activities here. It takes maybe 10 minutes to be stabilized again. So criticality means that. Self-organized means there is nothing from outside. It just does it itself. Okay. How much time do I have? 10 minutes. Okay, so I'm going to stay at this level of introduction and invitation. I'm not going to do a lot of maths here. Let me change this. Let me change a little bit this model. So this is a graph, right? This is a graph. It has vertices and it has edges, and it's a directed graph. So you know where you are going. You start from here and you are traveling this way. So you are not traveling that way, right? It's a directed graph. So if you are here, you are traveling this way. It's different than the previous one. It was not directed, right? The previous one was not directed. Now, let me do the same game with the directed graph, i.e., imagine you have 5 chips here and you want to move it. But you are moving it in the direction that it goes. So you cannot move it in this direction, right? Okay. Let's start again with the same story. Imagine you have 5 chips here. Okay, now I'm gonna introduce a little math. I write 5U for understanding. I have 5 chips sitting on the vertex U. Okay, so that 5U means that. All right, so can you start distributing? One of them goes here. Nothing goes here, right? Because they're directed graph. So one goes here, here it is, 1V. One goes back, so it doesn't do. So I get 4U plus V. So I'm here. Can you do one more? So now one is sitting here, but remember I have to have a lot of chips here, at least 3, as you see. So there is only 1, so I cannot move the one here. So still 1. But I have 4 here. So start again. One goes here, becomes 2V. One goes back, becomes 3U plus 2. There are 2 sitting here. I cannot do anything because there are 3 edges. But this one again, I can. So one goes here, one goes back. So I am here, 2U plus 3V. Now, let me introduce one more concept. And here it gets closer to casino and gambling. look at this one here. I call it sink, this vertex. And this is the game. If your chips gets here, you're gonna lose it. Okay, if your chip arrives here, you're gonna lose it. Okay. I was here. I have 2 objects here and 3 objects here. So there are 3 edges also. So the rule tells me I can move 2 of them here, 1 of them back. 2 of them here, 2 chips gets here. But remember, the rule was once you get to the sink, you are gonna lose it. So 2 of them gonna disappear, 1 goes back, so I get 3. Just keep doing this game. And if you just be patient and do this, at the end you get here. You get 1 object on you and 2 objects on me. And it stabilizes, you cannot move it anymore. You cannot move it anymore. Okay, so what I want to tell you here, as you see, you have to go back and forth to do this. It was not very straightforward, one. The other thing is all the theorems they proved I used here. One of them was, it doesn't matter which one I fire. I can fire this first and then this or vice versa. It doesn't matter. The other is that I always end up with this presentation. It's always a unique presentation. So I use both their theorems. Now, first time I'm going to introduce some monoid, and here are people who are quite expert in monoid, Rishabh, Ardeline, Nam, and a lot of people here work with that. So the monoid I'm going to introduce is, okay, so you have these vertices, UIs, and these are, the way I'm writing this, these are all the objects sitting on the vertices. Okay, this is the presentation I just write. So the way you understand this is that, okay, you have that many objects on these vertices. So if you have 2 of them, in algebra, I need to add things. Okay, here is the definition I gave you. Just, I'm sure if you glance at this, you can guess what I want to do. You add these objects, which are sitting on the same vertex together. So Ki plus Ki prime, sitting on Ui, and then stabilize them. So that's the addition. It's very simple, right? It's very simple and very natural. That's what I learned in maths. If you want to get results, you have to define in a very natural way. And this is the most natural way you can do. So there are that many objects sitting on these vertices. Again, that many objects sitting on these vertices. If you want to add them, just add the objects together. But now you have to see the complexity, because remember, I do this firing. So as you saw, I have to go back and forth. So although this addition is easy, but once I add and I start firing, this speed might be complicated. This speed might be that 1 million going there, okay? So again, the definition is easy, as always, but then the result you have to work on. Okay, good. So now let's go back to this very simple one. So whatever I get here, this domain, this monoid I just defined, I call it sand pile monoid. So sand pile, what was the story of this distribution? And I just defined a monoid, namely I can add things. So I call it sand pile monoid. Okay. This was introduced by Indian mathematician. I understand he is quite a celebrated Indian, in fact, not a mathematician, a physicist, called Dar. And I read recently he got some fancy prizes also from American Math Society. So anyhow, he defined this monoid 10 years after the first paper. Okay, so basically brought mathematics into this. Okay, so you have that. Now, this is my graph, this is my grid, and this is the notation of sand pile monoid associated to that, right? So as you can imagine, I can change this graph to whatever I want, and I get different mathematical objects. What you can see is that now I'm gonna in 5 minutes introduce a question that again nobody knows, and this is the question I want to ask you if you join us to solve. Okay, so you have a monoid. Inside this monoid, you have a group. If you're familiar with algebra, you can imagine what I'm saying. Okay, so you have a monoid, always come out of this graph, and inside it you have an algebra group. That means the elements have inverses. Now, remember this grade here. That grade at the very beginning didn't have exits. It's so that you lose your chips. Remember that we had a sink and you lose your chips? I'm going to introduce it here. So if you have a grade, at the boundary, I put these exits. So when your chips gets here, you're going to lose it. Can you see that? So if I get here and I have 3 chips, no, 4 chips, one goes up, one goes here, 2, you are going to lose. If you are here and you have 4 chips, one goes up, one goes down, one goes back, one you're going to lose. Okay, so I introduced these ones here. All right, so with this, let's do an exercise. Imagine I'm in this configuration. I think this is not going to move. So you have 2 chips here, 1 chip here, nothing here, and so on. So let me call this X. Now, I actually worked on this yesterday. Imagine you have this, and now write X plus X. Remember the definition of the monoid? You just have this, and then add on it 1 copy of X. So this becomes 4, this becomes 2, 4, 2, 4, and so on. Then becomes unstable because this is 4. So I start the process of firing, right? One more time. So this is X, X plus X, just add the numbers again. At some stage, this is 4. So remember these exits. So 2 of them disappears, 2 goes back and here. Okay, so if you keep processing this, and it takes maybe 2-3 minutes, you are back to X itself. And this is a good exercise to do, okay? So get X, add X, and convince yourself when you do all the process, you are back to X. In fact, that would be the 0 element of this. All right. Now, let me show you, that was a grid. I showed you this one, 2, 1, 2, 1, 0, 0. And if you add if you add this to itself, it becomes this again. For a 3 grid, 3 by 3 is this distribution. Okay. So this is the one that plays the role of 0. All right, so the way I write this now, I write it this way, 2, 1, 2, 1, 0, 0, 2, 1, 0. And then remember I gave a color to them. So I'm gonna give a color. So 2, I'm gonna put yellow. 1, I'm gonna put, I don't know, this blue and so on. 0, I put this black, and 3, this brown. So if you do this, you get this one here. This is the distribution of that 0 for a 3 by 3 grid. And this is what you get. Let's make it larger. This is what you get. Let me go one step further. Now it's getting interesting. This is a 10 by 10. This is a 25 by 25, 50 by 50, and this is the 0 element, the distribution of numbers, and I gave it color. And this is maybe 1,000 by 1,000. Do I have more? Yeah, this is 1,000 by 1,000. What do you see? What is common in all these pictures? What is it you see that common in all these pictures? Remember, these are different. This is 10 by 10. So forget the rest. I'm working on just this monoid here. This is a different monoid, which is 25 by 25. And I think maybe it's 500 by 500. And these are the 0 elements of these monoid. What do you see in common in all of this? What is it you see? Yeah, exactly. Exactly. Look, in all of these, this square appears here. So let me see, what color is this? Yellow, and the yellow is 2. So this distribution here, always, when you finish it, you cannot do any of these by hand. You have to use computer, right? When you finish it, they're all two. When you finish 100 by 100, they're all two and then different colors here. And it just keeps appearing, although, 1,500 and so on, always end up in the middle, they're all two. Okay, make it a bit bigger. Okay. And here is the question that, again, nobody knows. Why this distribution that always appears in the middle two? So in the boundaries are very, very nice fractal, but suddenly in the middle you get these twos. Why? Can you come up with a mathematical theory? You say, okay, look, I look at this monoid or I look at this group, because of some reason, it has to be all two in the middle. We don't know. All right, so I'm going to stop here. I'm sure people, maybe I'll just give you two books. There are two books. Here are the books. They are all both very, very nicely written. They are all new. And the chip firing, they use this terminology. The other sandpiles, as you see, both terminology are used. If you glance through these books, you see that this theory is connected to a lot of subjects in maths, in algebraic geometry, coding, algorithm, and so on. But still, they don't know why this phenomena happens. Explicitly, it was asked in this book. So maybe there is a different way. Maybe I can attach a different kind of maths to this phenomena and say, okay, because it happened there, something, then these twos appear there. So I want to show you at the very end. I'm going to skip all of these and go all the way to page 75. Because we are talking about Levy path algebras, and I did not mention one word about it. Okay. So you can connect the sandpile model with Levy path algebras that I'm sure my colleagues are going to talk about. So this is the work we did with Gene Abrams. Gene is in Colorado. That's one of the main places for Levy path algebra. So if you are doing Levy path algebra at some stage, you might go to Colorado. And so what we did is that if you start with the sandpile and you look at this monoid that I introduced, and then out of this monoid, there was this GE, the group, I call it here SPE plus. You can see that it's very closely related to these Levy path algebras that are the topics of this workshop. So somehow, and these are algebras, so somehow out of a graph, I get a monoid, and out of this monoid, I can connect it to an algebra. And we did some work also with NAM that we could connect the structure of this monoid with the ideals of these algebras. So who knows, maybe if I look at this zero element here, that zero element might give me some structure in this algebra. And by experience, these algebras are very well behaved. So maybe I can say why that distributions of two and this block of yellow happens, because in these algebras, maybe some ideals are dense. I don't know, I'm just throwing some ideas. So because nobody thought in these terms, I mean, these books, as you see, there are a lot of connection between sandpiles and other topics. So they have thought about that. But nobody has thought about connecting to Levy path algebras and explaining things here on this level. So that's why I invite you to look at Levy path algebra. It's very, very nice structures, and maybe they shed light to open questions here. Thank you very much.
If you have any questions, we need to have questions.
I answered all the questions.
Thank you very much. So, we can send in the question later. The next speaker today is I don't know about this. Professor Trần Giang Nam from Institute of Mathematics in Harvard.